you have more than one chiral center that you're looking at. But let's redraw D-glyceraldehyde as in the Fisher projection. Really what's happening here is that the groups that are on the horizontal line are on wedges. The old way to remember this is that they're coming out to hug you. So the hydroxyl group and the hydrogen they're pointing out. And then the groups that are on the vertical line are on dashes. So this carbonyl group is pointing down, CH2OH is pointing down. So now let's go ahead and prioritize these four groups using the language back from the first semester class. How about, let's use green here, of identifying the organization in that what was known as that Kahn-Ingold pre-log system. So we're looking for atomic number. So we have oxygen, that's priority 1. We have a carbon here at the bottom, carbon, hydrogen, carbon. So we know that these two carbons are going to be of a higher priority than hydrogen. So let's put that to be priority 4. Now we need to break the tie between these two carbons, and we look at what's attached to those carbons. And why don't we write it out here? Kind of keep track of what's attached to the carbon. And so this bottom one, let's do that first. It has a hydrogen, and an oxygen attached to it. The top carbon has a hydrogen, and then this carbon-oxygen double bond is treated like the carbon is bonded twice to the oxygen. It's just the way this notation works. It's like it has an oxygen and an oxygen. And then we look and see if there's something there that breaks the tie. If not, we'd have to go to the next carbon if that's an option. However, in this particular case, we see hydrogen, hydrogen, oxygen. Here we have oxygen, oxygen. We have 2 oxygens, which we don't have on the bottom. So that means this is going to be priority 2, this group, and this is going to be priority 3. Now, the trick with the Fisher projections are you could try to put this in a perspective so that the number 4 is in the back. Sorry, and I skipped a step, right? So the next thing is to put the lowest priority, which is this hydrogen, in the back. And then you would go around looking and seeing, is it clockwise, R, or is it counterclockwise, S? Now, with the Fisher projection, you have to be very careful because you can't just flip it around in some ways or rotate it. Otherwise, you're going to change the stereochemistry. You can turn it around completely. That's fine. But it gets to be pretty tricky trying to rotate this. And the thing is, you don't have to. This is where you can use a little trick to get the RS stereochemistry. Notice here, the lowest priority is actually coming out at us. So really what this means is we're going to end up getting the opposite stereochemistry if we would use this structure. But that's what you do here, is you just imaginarily, I'm not sure if that's the word, in an imaginary sense, you would then go through and say, okay, 1, 2, 3, it's going this way. So that would be S, with the H pointing out, which means I'm getting the opposite assignment. So in reality, it's R. And that's how we end up. That's a quick way to assign the stereochemistry. If the H is horizontal, is on a horizontal line, you get the opposite. Stereochemistry. We'll say stereochemical assignment. That sounds more impressive. So a couple of things to keep track of here to review. From this Fisher projection, the groups that are on the horizontal lines are coming out at us. The groups that are on the vertical lines are pointing away. So going to the top, coming out at us here, both D and L glyceride, these groups on the vertical line are pointing away. So to determine the R or S assignment, the easiest way to do it is to go through and assign priorities, 1, 2, 3, and 4, like we would do normally. And then as long as the lowest priority, which is usually a hydrogen, it doesn't have to be a hydrogen, but the lowest priority is on the horizontal line. When you go through the clockwise or counterclockwise motion, you get the opposite. And so here, that's why we had 1, 2, 3, we're going around. It's counterclockwise, which in the imaginary sense would be S, which means in reality it's going to be R. I'll scroll down a little bit. Hopefully that works. So on the, is that okay, Jenny? Can you see that there? Excellent. Okay, we're going to just scroll up just a little bit here. So then to use this L-glyceraldehyde to finish this point, notice now here's the chiral carbon that we're looking at with the red star. This is, let's put the numbers in there. This is priority 1. This is priority 2. This is priority 3 on the bottom. This is priority 4. If we were to connect them now, we're going around this way, clockwise, which is not the correct stereochemistry because the lowest priority is coming out at us. So we're going around in the R direction, which means in reality it's S. So the one on the left is R. That's the true stereochemistry. The one on the right is S. And these two compounds, since they are enantiomers of each other, one will be R, D-glyceraldehyde. One will be S, L-glyceraldehyde. So a lot to digest in terms of the stereochemistry. Did I address the question about which one is the R? So the one on the left, the R. Those are the real chemistry. So this is the real stereochemical assignment. This is where I would look out to the class to see if there's confusion or if people are. The bottom one, this one here is R. Oops. Is that okay? Okay, excellent. And then to the question, Paulina, about the positive and negatives. Again, this goes back to, remember in the good old days of Organic 1, I'll just put a little box over here, if this is enough. If you took a chiral compound, and don't want to drag you through too much of the detail, if you had it in a just my drawing of like a little cylinder that has the chiral compound in it, and you took light that is plane polarized, which I'm trying to show us up and down, so light that passes through a filter, so it's polarized only in one plane. When it interacts with the sample as it's going through the container that's holding the sample, so experimentally, it's going to get rotated into a particular direction. And so this is you not looking directly at it, but that's what it would, you're recording that. And you're going to record the rotation of the light. And this is a property of that chiral compound. And this is a way of experimentally evaluating chiral compounds. Now, the actual measurement is based on the concentration and the length of the tube and things like that. But for what we're concerned right now is that, let's just say, the R compound happens to rotate the light like in the right direction. Let's just say, I don't know what that is, but let's just say it's about plus 15 degrees in the right direction that the light is rotated. The S compound is going to rotate light 15 degrees as the absolute value, but in the opposite direction. So let's say it's minus 15 degrees. And I'm so used to, writing temperatures when I say degrees, so I put the C for Celsius. But so then what ends up happening is that if one stereoisomer rotates light in the plus direction here, that's why I'm here, I'm just making up this number of 15 degrees to the right, the enantiomer will rotate light in the equal and opposite direction. So minus, it means it's going, say, to the left, and the same magnitude, 15 degrees. So that's what the plus and minus here. It means that one compound is rotating light to the right. One compound experimentally will rotate light to the left. So it connects back to an experimental approach to evaluate chiral compounds. Okay. And then, if that all makes sense, one thing now to make it confusing is that R does not necessarily mean rotating to the right and S to the left. It happens to say work out in this case, but it's not like that for all compounds. But we're not going to really deal with that.